Hello, this is Joel Overton. The last video involved creating a group frequency distribution where we took this problem from your textbook, which is problem number 18 on page 61 from section 2.2, and we took this data and we organized it into this group frequency distribution. So that's where we discussed class width, how to use the class width to create these class limits, the lower and upper class limit for each of these classes, as well as tallying the data up to come up with the frequencies for each of these classes. From here, I'd like to continue on to create the class boundaries and then use the class boundaries and the associated frequencies for those classes to create a histogram. Now, the class limits themselves represent uniform, exhaustive, non-overlapping classes from which we can organize all of our data, which we've done. In other words, all of the data items should fit into one and only one of these classes, and all of the data items should fall into one and only one of these classes. There is a problem, however. For the data, all the data provided to us were given as nearest whole becquerels. In other words, all of these numbers are whole numbers. If someone were to have measured a piece of data as, say, 119.4 becquerels, 119.4 is not between 110 and 119, and it's not between 120 and 129. So it falls through 1 becquerel gaps between the class limits. Now, 119.4, you might look at that number and say, well, it's closest to 119, so it should go in these first classes. And that's true, but the reason why is because of the class boundaries. The class boundaries give us ways of closing the gaps between class limits so that they truly are non-overlapping and exhaustive. Just in case we do get measurements, we know exactly where to put them. Now, where are the gaps? Between 119 and 120, and between 129 and 139. In other words, 130. In other words, these gaps exist between the upper class limits and the next lower class limit. And once again, the gap is 1 becquerel distance, 1 unit of precision. So what we're going to do is take half of that gap, which would be 0.5, and subtract it from each of these lower class limits. We're going to take 110 minus 0.5, a half a unit of precision, which gives me a nice number here. Excuse me. So we're going to get my pen. 110 minus 0.5 is 109.5. And we keep on subtracting a half from each of these lower class limits. So 119.5, 129.5, 139.5, 149.5, 159.5, 169.5, and 179.5. Now we have what we call the lower class boundaries for each of our classes. Now, to get the upper class boundaries, so that we'll have these nice exhaustive intervals for our classes, we are going to add a half a unit precision to each of these upper class limits. So we're going to add a half to 119, which gives me 119.5. Then we'll add a half to 129.5 to get 129 to get 129.5, sorry. We'll add a half to 139 to get 139.5. And then we just continue. 149.5, 159.5, 169.5, 179.5, and last, 189.5. And now we have these class boundaries, so that if we did have measurements that had fractional parts, or decimals, we could figure out where they fall within this group frequency distribution. Now, one of the things I want you to observe that each of these class boundaries is 10 units distance apart. Each of the lower class boundaries are 10 units apart, a class width, and each of the upper class boundaries are also a class width apart, which agrees with the distance between consecutive lower class limits and consecutive upper class limits. So that's another way to verify that the class width is in fact, for this problem, 10, which is what was actually asked of you in the problem. They asked you to use a class width of 10. Now, when you're looking at these class boundaries, you notice that while the gaps have been closed, now you might be concerned about some overlap. Notice 119 is the upper class boundary for the first class, but it also is the lower class boundary for the second class. So what happens if you measure a child's teeth and get 119.5 becquerels exactly? Where does it fall? In the first class or in the second class? Because 119 is both of those. Well, in order to figure out which one of those it's going to fall into, you need to decide what convention to use for these boundaries. In other words, if X represents a data value or a measurement of radiation of strontium-90 in a child's tooth, then for the first class, we'll say X will fall in the first class if it falls between 109.5 is greater than or equal to 109.5, but strictly less than 119.5. So for the first class, if your data value is greater than or equal to 109.5, but strictly less than 119.5, it would be in the first class. So I'll say a data value in the first class is between 109.5 and 119.5. Then you use the same convention of inclusion of the lower class boundary and strict inequality of the upper class boundary for each of these. So the second class will contain any measurements between 119.5, including 119.5, and up to 129.5, but not including 129.5. It'll use the same convention. Now, once we've established these class boundaries, now we can create a histogram. And to create a histogram now, we need to start with a new page. But now, before I start drawing the histogram, I want us to recall something. The class boundaries themselves, if you look at the numbers themselves, you'll notice there are some distinct numbers being written here. 109.5, 119.5, 129.5, 139.5, all the way up to 189.5. So the distinct numbers involved, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 distinct boundary numbers. So I want to remember those numbers because we're going to use them to graph our histogram. And one of the things we'll need to reference back to are these corresponding frequencies. But let's start with 109.5 and start graphing the histogram. So I'm going to start a new note. And what I'm going to do is the following. I'm going to create some axes for our graph. Here's my vertical axis for frequency, and here's my horizontal axis for the class boundaries. And remember, our horizontal axis for class boundaries, our class boundaries are the amounts of strontium, right? I wonder what type of strontium that is. Strontium 80, strontium 90. Let's see here. Strontium 90. And the specific units were what? Millibecquerels. And sorry for my handwriting. Units of measure there. And we're going to need we're going to need 9 hash marks for 9 class boundaries. Here I've got 7. I need 8, 9 more. And I'm going to label these as well. And remember what our class boundaries were. Our class boundaries started at 109 and then increased by a class width, 10 units. So I have 109.5, 119.5, 129.5, 139.5, 149.5, 159.5, 169.5, 179.5, and finally 189.5. So there are our class boundaries. Also remember, we have frequencies as small as 1 all the way up to 13. So I need to give my vertical axis now, which represents number of children's teeth, or the frequency of our classes. I need to give hash marks that's going to accommodate values as small as 1 all the way up to 13. Now, I have 7 hash marks here. I'm going to say this is 2, 4, 6, 8, 10, 12, and 14. And now what I can do is I can create a histogram by extending vertical bars up to a height corresponding to the class boundaries. The first class, whose boundaries are 109 to 119.5, has a frequency of 2. Therefore, for my first class, from 109 to 119.5, I'm going to extend a vertical bar up to a height of 2. And just to make sure there's no confusion that that in fact is up to a height of 2, I'm going to label the top of that bar with a 2. Now the second class has a frequency of 2 as well. So I extend another vertical bar adjacent to the other one, meaning it shares its side with the next class with class boundary 119.5 to 129.5. I'm going to label that vertical bar 2. Notice there's no gaps between the vertical bars. They share, or they're adjacent to each other. The next class has a frequency of 5. So I extend a vertical bar up to a height of 5, which is halfway between 6 and 4, right? Now another thing you want to be careful about is that these vertical bars have the same width. This is a little sloppy here because I was a little sloppy with my hash marks, but you'll want to make sure your vertical bars have the same width. The only thing we're differentiating or contrasting between these vertical bars are their heights, which correspond to frequency. The next one has a frequency of 9, so I extend a vertical bar up to a height of 9, which is halfway between 8 and 10, so I made that one just a little bit too big. It's a vertical bar, and I'm getting sloppy here. I'm going to label this a 9 as well. The next class has a frequency of 13, so I extend a vertical bar up to a height of 13. Halfway between 14 and 12. I'm just going to label this 13, so there's no mistake. The next class has a frequency of 6, and then 2, and then 1. So let's do 6, 2 for the next class, and then 1, which is halfway between 1 and 2, right? And there is your histogram. Now, if you want to shade each vertical bar an alternating color or pattern, that's fine, but that's the extent of the embellishments you want to make to your graph. You don't want to do anything else. The only reason why I'm shading in alternating colors is so you can distinguish these bars a little bit more carefully, right? And this is your histogram. The only thing that's left for us now is to create a title for it. You always want to include the title for a graph because without it, you really don't have a very good graph. So this is what? The amount of strontium strontium 90 in deciduous teeth. That way, people can get a good impression of what you're talking about with the graph just by looking at the title. One more thing, you should include in every graph the source of your data. Like a citation, without the source, your graph is incomplete. For this, I'm just going to sort the